Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 1, Lesson 8 on multiplying binomials. So this is one of those topics that we'll actually be using a lot more in later units, but it flows really nicely from what we've been doing so far in Unit 1 with equivalent expressions and properties of real numbers like the distributive and the associative and all of that. So let's get right into it. All right, binomial expressions. These are some of the most important expressions in all of math. And recall that all a binomial expression is any expression with exactly two terms, right? And you can really think about it as sort of like an expression that has either a single addition in it or a single subtraction in it. And these types of expressions are very, very important in algebra. They come up all the time. Here are some examples, right? X plus 8. The two terms are x and 8, and they're being added together. 3x minus 7, the two terms 3x and 7, and they're being subtracted. N squared minus 9, same thing, a cubed plus b cubed. So expressions that involve two things being added or subtracted, two terms, I shouldn't say things, two terms being added or subtracted are known as binomial expressions. And today what we're going to be working on is how do you find their product? And believe it or not, this is not very different than how you find the product of two-digit numbers. So let's get into it a little bit. All right, here we go. Products of binomials. Finding the product of two binomials is a very common skill needed for algebra. When we find a product, we are looking for an equivalent expression. Remember, it doesn't do us any good to find a product that has the variables in it again if it's not equivalent to the original thing. So let's take a look at exercise number 1. Consider the product x plus 3 times x plus 5. It is equivalent to one of the expressions below. Determine which by substituting in two values of x to check. All right, so again, keep in mind what equivalent expressions are two algebraic expressions that when you put in the same value of x to each one of the expressions, their values are equal. So let's do it. Let's put x equals 3 into all three expressions, work out what their value is, and see which one of these two, right, is equivalent to this one. We'll do it together for x equals 3, and then I'll have you do it on your own for x equals 5. Let's go to the board. All right, so let's put x equals 3 into this expression and see what we get. We get 3 plus 3 times 3 plus 5. 3 plus 3, I almost just said was 9, but in fact it's 6. 3 plus 5 is 8, and 6 times 8 is 48. Mental hiccup there. All right, let's put x equals 3 into x squared plus 15. Well, that's going to be 3 squared plus 15. That's going to be 9 plus 15, right? 3 times 3, and that's going to be 24. And finally, let's put 3 into this more complicated trinomial. That's going to be 3 squared plus 8 times 3. Notice how I keep putting the 3 in parentheses. It kind of gives me a good place to be able to put that input. 3 squared again is 9. 8 times 3 is 24. Plus 15. 9 plus 24 is 33. Plus 15, and that is 48. So let's step back and take a look at what we've seen. All right, it sure seems like x plus 3 times x plus 5 might be x squared plus 15, right? Because x times x is x squared, and 3 times 5 is 15. And yet, when we put x equals 3 into this expression and this expression, we got very different values, 48 and 24. Don't take anything from the fact that this one was half of that one. That was just a coincidence. Now, on the other hand, when we put this into this more complicated expression, x squared plus 8x plus 15, we got exactly the same value, telling us that it's probably the case that this expression and this expression are equivalent. One thing we know for certain is that this one and this one are certainly not equivalent, nor are this one and this one. So what I'd like you to do is do exactly what we did, but use x equals 5, evaluate the three expressions, and let's see if the first one and the third one continue to be equivalent. Pause the video now and go ahead. All right, I shouldn't say continue to be equivalent. Look, two expressions are either equivalent always or they're not. Do you know what I mean? Now they can be equal, right, at one value of x and then not equal at another value of x, but that would just mean that they're not equivalent. All right, let's go through it. Let's see what we get. I'm going to bring this up a little bit so we have a little more room to play. All right, I'm going to put in 5 plus 3, times 5 plus 5. All right, 5 plus 3 is 8, 5 plus 5 is 10, and 8 times 10, last time I checked, was 80. All right, let's put 5 into this expression. We get 5 squared plus 15. 5 squared is 5 times 5, that's 25. 25 plus 15 is 40. Now I'm starting to think those are always half of one another. And finally, or maybe they just are for that value, the more complicated expression, we're going to get 5 squared plus 8 times 5 plus 15. 5 squared, 25, 8 times 5 is 40, plus 15, 25 and 40 is 65. 65 plus 15 is again 80. All right, so we now have some good evidence that the first expression, x plus 3 times x plus 5, is equivalent to the last expression, x squared plus 8x plus 15. We've got evidence, right? We have not proved that they're equivalent, but we definitely have evidence. And we know for certain one thing, which is that x plus 3 times x plus 5 is not x squared plus 15, right? If those were equivalent, then the values that we came up with here would be the same as the value that we came up with there, and they aren't. So let's take a look at how we multiply binomials. Now clearly, when we multiply binomials from that last exercise, we can't just multiply the first terms together and multiply the last terms together and then add them or subtract them or whatever. That doesn't work. So let's take a look at the algebraic procedure. This is what's called double distribution. Let's take a look at the algebraic procedure for how we can get from x plus 3 times x plus 5 to its equivalent x squared plus 8x plus 15 form. And let's talk about and justify the steps, right? Just like before, let's kind of do this together, right? That first step is just our x plus 3 times x plus 5, right? And then I've rewritten it as x plus 3 times x plus x plus 3 times 5. So what property, right? We've got associative, commutative, distributive. We've also got an exponent property. What property justifies that? Think about that for a moment. Well, it's the distributive property, right? All I'm doing is I'm looking at x plus 3 as a single thing, and I'm distributing it through. That's it, right? I'm taking my x plus 3, and I'm saying, well, let me multiply it by x, and let me multiply it by 5, right? So that's just the distributive property. All right. Now, in step 2, like all of these problems, this has just been reproduced down here. And now it said, okay, now I've got like x times x plus 3 times x plus x times 5 plus 3 times 5. So what justifies that? What allows me to do that? Well, that is the distributive property again, hence the name double distribution, right? In fact, what I've done is I have multiplied this x through here to get x times x plus 3 times x, and then I've distributed the 5 through here to get x times 5 plus 3 times 5. So yet again, that is the distributive property. And finally, to just hammer this all home, right? Then what I've done is I've taken my 3 times x plus x times 5, and I've rewritten it as x times 3 plus 5. And that is yet again the distributive property. You might just say, well, you've combined like terms. And that is to a certain extent true, right? 3x plus 5x is simply 8x. But remember, the reason that we can do that is due to the distributive property. So there's just a whole lot of distribution here, right? Granted, the first two distributive property steps, those were sort of the distributive property, in the forward direction, i.e. taking a binomial and multiplying the binomial through by something that's multiplying it, okay? This last use of the distributive property was more about factoring an x out of these two terms to allow us to combine like terms. Okay, now we want to be able to justify those steps, but what we really want to be able to do is find these products. Let's get some practice on that. All right, to multiply two binomials, we're really just using the distributive property twice, or 3 times maybe. This is very similar to how you multiply a pair of 2-digit numbers together. Okay, so let's get some practice on this in exercise number 3. Let's take a look at letter A. X plus 6 times x plus 3. Okay, now when I do this, I want to look at this x plus 6 as if it's just a number. 5, 10, 2, -7, whatever, right? So the idea is I'm going to start by taking this and multiplying it through. Now what does that look like? Well, it looks like this. X plus 6 times x plus x plus 6 times 3, right? I'm allowing both the x and the 3, the x plus 3, both of those are getting multiplied by x plus 6. Now I use the distributive property and I multiply both of these terms, x plus 6 by x, giving me x times x, which is x squared, x times 6, which is 6x. Now I'm going to multiply both of these two by 3. X times 3 is 3x. 3 times 6 is 18. And what will always happen in these problems is that the middle two terms will be like terms. 6x plus 3x is 9x. Whoops, and I almost wrote 15, where in fact it's 18. So I get x squared plus 9x plus 18. That's it, right? Simple enough. Let's do letter B together because it involves some negatives, okay? Let's go to the board. X minus 4 times x plus 9. Again, I'm going to take that x minus 4 and I'm going to distribute it through. So I'm going to get x minus 4 times x plus x minus 4 times 9. All right, I'm going to then distribute this x through. I'll get x times x, which is x squared, minus 4 times x, which is 4x. Distribute the 9 through, right? Then I'll get 9 times x, which is 9x, minus 4 times 9, which is 36. Notice again, those two middle terms are like terms. A negative 4x and a positive 9x gives me a net positive 5x. And I get x squared plus 5x minus 36. All right. Now, what I'd like to do, I'm going to leave letter C for you, but I'd like to do letter D together and then have you do C, E, and F. So a little bit of a different order here. Let's tackle letter D together. So far we've been doing these problems where it's all like x plus this, x minus that. Here I've got some 2x and some 3x going on. But the idea is still the same. I'm going to multiply both the 3x and the positive 1 by 2x plus 3. Right, I need to multiply both of those. Now I'm going to distribute the 3x through. So 3x times 2x is 3 times 2, which is 6, and x times x, which is x squared. Then 3x times 3 is going to be 3 times 3, which is 9, and then I just have x to the first. Of course, this is going to be pretty easy. I'm going to multiply through by 1. 1 times 2x is 2x, and 1 times 3 is 3. Now I've got those middle two terms, which are like terms, and I'll get 9x plus 2x is 11x plus 3. Okay, simple enough, right? 6x plus 11x plus 3. So what I'd like you to do now is pause the video, all right, and work on letter C, E, and F, then unpause the video and we'll come back and we'll go through them. All right, let's do it. Now, x minus 3 squared. That can be tricky for kids, but never forget what exponents tell you, right? They're not just little numbers that are hovering above something, right? X minus 3 squared literally means x minus 3 times x minus 3. That's just what it means. It's what it tells us, right? So I'm going to write that down right here. right? And now it looks exactly like the other problems I've been doing. I'm going to take this x minus 3 and I'm going to distribute it, right? That's going to give me x minus 3 times x, all right, minus x minus 3 times 3. Actually, I'm going to put plus x minus 3 times negative 3. I think that'll be an easier way for us to think about this, right? I can always change subtraction to addition of a negative. So now we'll distribute that x. X times x is x squared. X times 3 is negative 3x. Now I'll distribute this multiplication by a negative 3. Negative 3 times x is negative 3x. And negative 3 times negative 3, watch out for that, is positive 9. Here we've got like terms again. Watch out. We don't have 3x minus 3x. We have negative 3x and another negative 3x. So that's going to be negative 6x and then plus 9. All right. Let me move the board up a little bit. Let's talk about this one. 3x minus 4 times 3x plus 2. Give myself a little more space. Again, double distribution. We're just going to distribute the 3x minus 4. 3x minus 4 times 3x, whoops, times, let's try that again, times 3x plus 3x minus 4 times 2, just fit in there. Now we'll have to distribute this. Starting to wonder if this should be called triple distribution. All right, 3x times 3x is 9x squared. 3x times negative 4, negative 12x. 2 times 3x is 6x. 2 times negative 4 is negative 8. Again, combine those like terms. Negative 12, positive 6 is negative 6, and minus 8. All right, final problem. Lots of negatives involved here. I'm going to distribute that 4x minus 1. I have 4x minus 1 times x plus 4x minus 1 times negative 7. All right, distribute the x back through. Distribute the negative 7 back through. I have x times 4x, 4x squared, x times negative 1, which would be negative x. Negative 7 times positive 4 is negative 28x, and negative 7 times negative 1 is a positive 7. This is a little tricky. I've got 1 negative x and I've got 28 negative x's, so I've got 29 negative x's plus 7. Negative 29x plus 7. All right. You know, every once in a while I say, Kirk, you should be consistent about whether you circle your answers or put them in rectangles, and then I'm not. And what can you do? At least you know where the final answers are. All right, let's do a little bit more about this. All right. Now, I gotta figure out a good place to put this. Algebra can oftentimes help us understand patterns that we notice with numbers. Different forms of expressions can reveal why certain calculations work out in certain predictable ways. And this is really kind of cool. So let's take a look at exercise number 4. Jameer has noticed a pattern that he thinks is always true. If he picks any number and finds the product of one number larger and one number smaller than it, the result is always one less than the square of his number. All right, and letter A says, test some numbers out and see if Jameer's pattern holds. So this is cool, right? All right, so let's talk about this. Jameer has figured out that if he grabs a number like 10, let's go with 10, right? And he picks one number smaller than it, right, which is 9, and one number larger than it, which is 11, and he finds their product, which is 99, that's going to be one less than the square of the number, right? So this product, make that dot a little bit bigger, will always be one less than the square of the number. Well, let's see, 10 squared minus 1. 10 squared is 100, minus 1 is 99. Ooh, yeah, so it worked there. Now, maybe I was just being a little shifty and I just grabbed, 10 because I knew it would work with 10. What I'd like you to do now is pause the video, pick a number, literally any number you want. It could be positive, it could be negative, it could be fractional. Yeah, go really bad. Go fractional. Don't go fractional. Pick something nice. And try to see if Jameer's pattern holds. Pause the video now. All right, I don't know what number you picked. I'm not a magician. But let me grab with something. I like lucky number 7. Let's go with 7. All right, so let's say I start with 7. Remember, Jameer's pattern was if I took one number less than 7 and one number more than 7, and I found their product, which is 48, somehow that would be equal to my number squared minus 1. That looks like 72. Let's do this. Well, 7 squared, man, this is just getting worse and worse for me. 7 squared minus 1. 7 squared is 7 times 7, which is 49, minus 1 is 48. And it's still the same. So why is this, right? I mean, and we could choose number after number after number, and we would see that if we take the product of one number less with the product one number more, we will always get the square of the number minus 1. Let's take a look and prove that in letter B. Let's take a look. Letter B. Give an algebraic explanation that shows that Jameer's pattern will work for any number. Use let statements to clearly define your variables. All right, since this is the first time we've done something like this, let's do it together. All right, here we go. Right, so I want to, let's do, I like n. Let n be equal to the number. Now remember, Jameer's pattern involved a number that was one more than it. Right, so that would have to be n plus 1. And then let's let n minus 1 be 1 less, right? So there's our let statements, right? N is just that arbitrary number. N plus 1 is 1 more than the number. N minus 1 is 1 less than the number. Now remember, what Jameer figured out, or what he observed, was that when I did the product of this with this, I always got 1 less than what I would have gotten had I squared this number and subtracted 1. So, if that's the pattern, let's find the product of these two, right? So, let's find the product of n plus 1 times n minus 1, and let's see what we get. Now, this is the tie-in to the lesson itself. We have to do this by using double distribution, right? So what I'll get is n plus 1 times n plus n plus 1 times negative 1. All right. I can now distribute my n on through, and I can distribute my negative 1 on through. And I'll get n times n, which is n squared. I'll get n times 1, which is plus n. I'll get n times negative 1, which is negative n. And then I'll get 1 times negative 1, which is minus 1. And I want to pause just for a minute right now and talk about how we finish simplifying this. Right, I've got n squared plus n minus 1. Well, anytime I have a quantity minus itself like that, n minus n, well, that's just 0, right? So I ultimately get n squared minus 1. And that verifies Jameer's pattern, right? He knew that if you did the product of 1 more times 1 less than a number, you would always get the square of the number minus 1. So that algebra is showing us that any number we would have picked would have fit this pattern because it is an algebraic certainty. All right. We'll play around with some more algebraic puzzles towards the end of Unit 1. All right, but we definitely want to make sure that we've got this process down of multiplying two binomials. And it's important to remember that when we multiply two binomials, the result is an expression that is algebraically equivalent to the original product, just written in a different form. All right, so let's take a look at one last exercise on this, and then we'll finish up the lesson. Exercise number 5. Which of the following expressions is equivalent to the product x minus 2 times x minus 4? Show the work you use to find your choice and test for equivalency using the value x equals 5. All right, well, take a moment, try to find the product of these two binomials, see which one of these 4 choices you think is correct. Once you think you have the right answer, then take x equals 5, substitute it both into the original expression and whichever one of these things you think is correct, and see, do they have the same final value? Pause the video now and go ahead and try this. All right, let's do it. I'm gonna move this down here a little bit. All right, I've got my x minus 2 times x minus 4, a little double distribution. We're gonna take this, multiply it on through. That's gonna be x minus 2 times x plus x minus 2 times negative 4, right? We're then gonna distribute this and distribute this, right? I have x times x, which is x squared, x times negative 2, which is negative 2x. Negative 4 times positive x is going to be negative 4x, and negative 4 times negative 2 is positive 8. Very important. Negative 2 times negative 4, positive 8. Negative 2x and negative 4x combine to be negative 6x. And there is the equivalency, and that is choice 3. The major mistake students will make on this problem is that they will say negative 2 times negative 4 is negative 8, right there, okay? And you have to watch out for that. Now, if you tested for the equivalency by what we're going to do next, and you thought it was this one to begin with, you would find out very quickly that it couldn't be that one because they'd have different values. Anyway, let's test that equivalency as our last thing of the lesson. All right, so first thing I'm going to do is I'm going to throw my x equals 5 into the original expression. So that's going to be 5 minus 2 times 5 minus 4. That's going to be equal to 3 times 1. And last time I checked, that's equal to 3. Right? So let's take a look at the equivalent one. We hope it's equivalent. Maybe I should call it the manipulated one. I don't know. That's this one. So now I'm going to take my 5. I'm going to square it. Minus 6 times 5 plus 8. 5 squared is 25. 6 times 5 is 30 plus 8. 25 minus 30 is negative 5 plus 8. And negative 5 plus 8 is 3. And so that reinforces the idea that these two are equivalent. Again, had we made any mistake and taken that 5 and plugged it into here and plugged it into any of the other 3 choices, we would find that they didn't have the same value and therefore couldn't be equivalent. Okay, let's wrap it up. Multiplying binomials, right? A binomial is an algebraic expression with 2 terms. Multiplying binomials comes up more than you can possibly imagine in algebra. It's in algebra, it's in geometry, it's in algebra 2. I mean, it just happens a lot. And we're going to develop various methods for multiplying binomials that we're going to give you quite a few tools in your toolkit. All right, double distribution is just one of them. But what I don't want you to ever forget, right, is that what we're doing is we're coming up with an expression that is equivalent to the original product, and that is hugely important. We'll see a lot more of this skill as we move forward. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.